Okay. So in the class last time we started talking about network edge stuff. So our hosts, the end systems, the physical networks, wired, wireless communication links, so that goes between those, and then the network core, which is our pieces of hardware that we're familiar with, routers, and we talked a little bit about network of networks last time. I think I asked the question, what was a router? Did somebody give me an answer? Was it a good answer? I think somebody maybe said something along the lines of a router divides a network from another network. A lot of times we can call them firewalls. Okay, so that's what a router is. Modernly, when we go and buy a router from Best Buy or something like that, we typically think of routers having some additional abilities. They also have software built into them for like running a DHCP server for handing out IP addresses and some stuff like that. We'll talk about those things, but a router itself is really a division point between an internal network and everything that's outside of it. Okay? And when you have networks of networks, like we mentioned we have here on campus, you might have several routers around campus with a single edge router which blocks campus from the rest of the world. Let's see, I already basically said that. Okay, so this is kind of an interesting thing maybe to discuss a little bit when we talk about bandwidth. So last time we were talking about bandwidth and we were talking about latency, where bandwidth is how fast data travels on a network, and latency is how what the turnaround time is to go from an endpoint back to where you started. Now, let me say this again. Latency is how fast it travels. Bandwidth is how much can travel. Latency is how fast it can travel. Bandwidth is how much is traveling. Okay, so a car can travel at 100 miles an hour. That's its latency. But higher bandwidth would be a semi than a smart car. More data is moving. Now, having said that, typically when we think about bandwidth, we're thinking about it in terms of our internet connections, right? We are concerned about bandwidth in terms of how fast can we download stuff off the web. But bandwidth plays into more than just that. What's the bandwidth of a local area network? So if I have two computers, so let's just take that lab down there. Let's say we disconnect it from the internet. Okay, we're not on the internet. But all those computers are still networked together. And I want to send data from one of those machines to another machine. Okay? Somewhere there's a router that's blocking that lab off from some other part of the network. And then more locally, we probably have something called a switch. Okay? Now, the switch is what interconnects all those guys so they all can see each other. We'll talk more about that. But regardless, if I have one computer down there and I want to send a file to another computer down there, are we using the internet to do that? We're using the local area network, right? How fast do you think data moves between two computers down there? Does it depend on the computers?
The routers, the network cards.
Probably depends on the network infrastructure that those machines are plugged into, right?
Okay.
I mean, historically, you might have said it would depend on the computer. Anymore today, most of our default network interface cards are not going to be the limiting factor. You know, back 20 years ago, you might have a Ethernet card in your computer that was only capable of 10 megabits per second. And if it was on a 100 megabit per second network, it was only going to play at 10 megabits per second because of its limitation. By today's standards, at least from consumer level networks, our machines probably have up to gigabit Ethernet or 802.11, at least N, probably wireless. So pretty much at the top level of what you'd see in consumer type applications. But the limiting factor down there is going to be how the wires between those machines are connected and what technology supports that, right? So now Val is going to know better than I do, but my guess is we probably have a gigabit switch between those. Is that accurate? Okay, so we have a gigabit switch between well, all those machines are using Ethernet. They're plugged into a central gigabit switch. So that creates a total network bandwidth of 1 gigabit. Okay? So that means that one of those machines can transfer data to another one of those machines at a maximum speed of 1 gigabit per second. Now, what things are going to interfere with that? When we talked about downloading stuff from the internet, we talked about asynchronous internet connections. We were talking that, okay, well, my download speed is limited by whoever I'm downloading from's upload speed, right? Well, we just said that both the upload speed of one of the Macs down there is 1 gigabit per second, because I'm sure they have gigabit Ethernet cards in them. The download speed of the one next to it that we're transferring the file to is 1 gigabit per second. So that would be a synchronous connection, correct? Upload and download speed are the same. So they're capable of doing 1 gigabit per second. No harm, no foul. The network that they're transferring the file on is capable of 1 gigabit per second. Would I get 1 gigabit per second data transfer? Maybe.
Who else is using the...
Okay, potentially who else is using the network? Okay, let's say we're the only ones. Only ones actively using the network. What other things might slow down that transfer?
What other processes you're running on the computer slow it down?
Potentially if we have more than one thing utilizing the network card. You know, if we are downloading a file off the internet at a certain speed, which isn't going to come anywhere close to 1 gigabit, at least today, now we're sharing our maximum bandwidth for our network interface card between those two applications, something like that. But something we're going to end up talking about in this course is this idea of TCP/IP. The protocol, the language that governs us sending files from one of those computers to another computer over an Ethernet-based network in such a way that we guarantee that the data doesn't get broken. Okay? So, as human beings if we're moving data from one of those computers to another computer, do we care more about speed or that it doesn't get corrupt? We don't want it to get corrupt, but we want it to go as fast as humanly possible without getting corrupt. Those are two goals, right? We'd rather it go slowly and not get corrupt than be really impressive and unusable. Make sense? Okay, so one of the jobs of TCP/IP is to ensure that more than one machine, or I'm sorry, to ensure that data that's being transferred from one machine to another does eventually arrive at its destination. One of the things that can happen on a network like this is collisions. We talked a little bit about this last time. I think I used the analogy of a interstate. And if everybody's heading north, blocking up the entire interstate, and we're heading south in a single car, and we're driving recklessly, the chances of us colliding with another vehicle is pretty high, right? Okay, well, you know, when you're talking about data flowing around on Ethernet cables, they're not veering around other cars. Okay, these are electrical signals flying along copper wires or potentially fiber optic cables. The chances of it bumping into another piece of information is reasonable. And when that happens, things get destroyed and have to be then resent, stuff like that. So that network down there can support transferring stuff at 1 gigabit per second, but realistically, you're probably not going to get a sustained transfer of 1 gigabit per second because there's overhead over and above that that's governing the accuracy of that network, specifically in this case TCP/IP, which has a whole bunch of checks and balances to make sure crap doesn't get broken. Fair enough. So it's going to go a little slower than 1 gigabit per second, but you also know that when it finally gets there, it's correct. Okay? Now, having said that, do you think you're going to be faster? So let's throw a scenario here. We're going to download an operating system onto one of those machines. Okay, we'll use, so let's say you want to install Yosemite on all those machines. Yosemite on all those machines. Okay, so we're going to download it on one computer. Now, we want to go and get it on all the other computers. Our options are to go to each computer and download it off the internet. Another option is to go download it once, put it on a jump drive, and take it to each computer. Or our third option might be, download it on one computer, put it onto burn it onto a DVD. Do those have all but the thin ones have drives, right? Okay, so we're screwed on two of the machines, but let's pretend that's not the case. So we can burn it onto a DVD and then take that DVD to each machine and install the operating system. Or we can share that file over the network. Which is the correct solution for that problem? They will all work, except for the couple of machines that don't have an optical drive.
Well, if they don't have it, do they have an OS on, or are you talking?
Sure. Let's say they're all running. Yeah, we're upgrading it.
Okay.
They're all running the previous operating system. We want to throw Yosemite on there, and so we need to get the software into each of those machines so we can start the installer. What's the correct solution to that problem? Okay, some of us are IT majors, some of us are computer science majors, but regardless, this is something that you very well might have to do. You might have to install an operating system on an entire lab. Now there's some cool pieces of software that let you multicast something out to every machine in the lab and that kind of stuff that is made for solving this problem. But we're going to do this, we're going to shoot from the hip here. Okay? We're kind of doing this one machine at a time or a couple machines at a time. We want to try to be as efficient as possible. Which of those solutions are you going to pick to get Yosemite on all those machines? And why?
So is the source OS coming from an external source, you said?
Yeah, we're downloading from Apple, which has a pretty fast upload speed, but not 1 gigabit. You won't download it from Apple at 1 gigabit.
Those have USB 2.0. Write speed of a drive is going to be slower, plus the time it takes to do the drive.
Write speed of what drive?
Of the DVD drive. If you do it through a DVD, it's
okay.
Slower than USB 2.0.
Okay, so you're cutting out DVD right off the bat.
Yep.
Okay, you're saying burning it to a DVD is going to be slower than copying it to a jump drive.
Yep.
USB jump drive. Okay, fair enough. DVD's off the table.
If it's
good news too, because 2 of those machines it wouldn't have worked for anyways. All right.
USB 2.0, you're going to run into there's a speed thing there too. USB 2.0 is what not even 100 megabits per second.
Faster.
Faster.
Yeah, USB 2 is I think 800 megabits per second.
And then USB 3.0 is going to be faster.
It's faster than that.
Okay.
USB 3.0 I think starts at 3 gigabits per
3
second.
gigabits, yeah. So your best idea. Well,
let me ask you this before you go too much farther there. Is the communication channel between that machine and a jump drive, a USB stick, is that a network in and of itself?
Yeah.
It's a communication channel between 2 machines, right? Okay, and it had a speed associated with it, right? So those machines down there are running USB 2. So if you have a USB 2 jump drive that has a maximum speed of 800 megabits per second, maximum. Okay, USB is a parallel-based technology, so it's bursty, as opposed to a serial-based technology. So maybe you'll average 500 megabits per second. Megabits, not megabytes. 500 megabits per second, let's say. Okay, so that's one option. What's the other option? Copied over the network? Yeah. What do you think?
You didn't rule out downloading yet.
Yeah, we didn't rule out downloading yet.
Downloading it individually on each might be the best.
You think?
Well, you could do them all at once.
Okay. So how many machines do we have down there? 20? 22? 25 machines. We have 25 machines down there. We're going to download Yosemite on, we already have it on one of them. So we decided the best way to get it in the other 24 is to download it on the other 24, as an example.
Yeah, the router's going to evenly distribute the most amount of power it can to each machine.
Okay.
So overall...
Well, how fast are we going to get it from Apple?
Pretty fast. It's Apple.
Mm-hmm.
It's on release date.
It's our download limit. What's the maximum bandwidth download that we have here on campus? What's campus capable of?
100 megabits on a good day.
Huh? 100 megabits on a good day?
Yeah, 2.5 megs per second.
2.5 megabytes per second is slower than 100 megabits by a lot.
So, yeah, I mean, it's not fast.
Yeah, 2.5 is what, about 20 megabit?
Yeah.
Give or take, somewhere in that ballpark.
Not
So we can download at 100 megabits per second, but across all those machines. But that's 100 megabits total per second, maximum, across all those machines. Not per machine, across all of them. Because that's the speed of Concordia's internet pipe, which then is going to be distributed amongst all those guys. Now keep in mind also that we're bringing in all this data. First of all, we're duplicating data, right? We have a bunch of data coming over the network from the same source, So we have a whole bunch of, we're going to learn about these, a whole bunch of packets flying around. These guys are smashing into each other.
You get an increased chance of corruption.
More collisions, because now you have all this stuff, all these machines downloading at the exact same time, a whole bunch of data, a constant stream of data that might take several hours to download on the same switch with all these packets of data flying by each other, possibly colliding. Bad news, right? Okay. Besides that, you're also at a random, you're in a situation where you don't know when Concordia's internet's just going to go out. Happens, right? Okay. So given that, is downloading maybe out? Sharing it over the network. What do you think about that? Is that going to probably be our fastest option down there? It's on a local network. These guys are basically tethered to each other. Just like borrowing butter from your neighbor. Okay? You're going to be able to move them pretty quickly. So how big is the operating system? Let's just say it's a 4 gig download, 4 gigabyte download. Okay? How long will that take to transfer 4 gigabytes of data from one machine to another machine at 1 gigabit per second? Let's go that route. 1 gigabit is how many gigabits? I'm sorry. You like that? It's a trick question. The correct answer is 1. Correct answer is 1. 1 gigabit is how many megabits? 1024, right? Okay, so we have a 4 gigabyte file. 4 gigabyte file that we need to transfer at a speed of 1 gigabit per machine. How long is that going to take? How many megabytes are in 4 gigabytes? 4,096? So 1,024 times 4? So 4,096 megabytes. How many megabytes per second are we transferring at 1,024 megabit?
128 megabytes.
So 128 megabytes per second. So 4096 divided by 128 is 32 seconds. So best case, no network slowdown. It will take us 32 seconds to move the entire file that we downloaded of Yosemite on one of those machines to another computer. 30 seconds. It's pretty fast, right? No big deal. So in 10 or 15 minutes, we could probably have it on the local drive of every one of those machines. Right? Ish. Something like that. Okay. Well, is that pretty good? A lot better than downloading it 25 times, right? Okay. What about putting it on a jump drive and taking it to each machine? Jump drive wouldn't have been horrible. Wouldn't have been fast either. Now, what if you had a bunch of jump drives? While it's copying on one, you could have been copying it onto another. So you actually keep doubling your number of jump drives that it's on. You actually, through perseverance, you potentially could be competitive in this race. Given enough jump drives. Given enough jump drives. Okay, but from a convenience perspective, having one of those machines shared on the network drive, we can then go to each machine, find that network share, just drag it onto the local disk. Done. Right? No harm, no foul. Now, are we better off dragging it onto the local disk or just installing it directly from the network drive? Okay, so we can go onto the network drive and we can see that file being shared, right? And from our perspective, it just looks like it's a local, here, let's see if we can find one on here. See if anybody's sharing anything. Well, we'll pretend like somebody was sharing something right here. in the public share. If we had their account, we'd probably log in. But we'd see an icon right here. I could double click on it and run it, right? Now let's say that was a computer program like, I don't know, Notepad, relatively small application. Is that okay to run over a computer network? Well, but when you're using Notepad, do we want it to be slowed down by a network? It won't be. Once we double click on it, it's going to stream it over the network and load it into our local RAM. We're only going to be using the network again if we go to save a file and choose to save it on a network drive. Once we've double clicked on it and it's launched into our memory, it's local. So something like that, launching off a network drive, is not a big deal. Maybe it takes fractionally longer to launch off the drive. If it's a really big file, it might take a lot longer to launch off the drive. But once it's launched, it's fast. Okay? Same example could be used if any of you in the IT world have ever had multiple operating systems installed on external drives. You know, whether you have a version of Windows 8 or Windows 7 installed on a USB drive, or you could even do it on a jump drive, but let's say a USB external hard drive. When it first boots, it boots a lot slower, right? But once the operating system's up and running, it's relatively fast, isn't it? The only time it's having to go rewrite stuff to the slow external USB drive is when it's doing log files and stuff like that, really small pieces of data. Most of the time, once it boots up slowly, we experience a pretty full-speed operating system. That's the whole argument when people are building new computers today. You know, if you're building a new computer, you spend, you want to get a solid-state drive, relatively small one, to be your boot drive. And then you can go get your 3 terabyte hard drive that, who cares how fast it is, for all your crap to sit on it, right? Because you want your operating system to boot fast. What?
The illegal files.
The illegal files. Yeah, the 3 terabyte drive is for your illegal files. All right, and the idea is that it's sitting out there, and when you're saving stuff to it, you're not experiencing the fact that it's slower than your solid-state drive. What you experience from your solid-state drive is how fast your operating system boots. Maybe you put a couple of the applications you use often on the solid-state drive so that when you double-click on it, it launches quickly. It's all your gaming. Like all your gaming. That's all you're gaining. It's all you're gaining from it. Okay? Speaking of gaming, are you better off putting your games on that solid-state drive? Would you gain performance that way?
Your load times will be faster, but the overall, well, it depends on the game.
Okay, tell me more about that.
Like if it's World of Warcraft, your load screens are going to be faster on it, but it has to have network capabilities to contact across the server to their servers. Yeah, textures are a little faster.
I would say for most modern games today, they're reading and writing from disk often. Okay, games are pretty hard on your hard drives. So installing your game on a solid-state drive is going to give you a pretty noticeable performance boost over that same game being installed on, let's say, a relatively slow mechanical drive, like a 5400 RPM drive or something like that. Just, if you're really trying to really see the experience difference, you'll notice. Okay. All right, so when we think about bandwidth, I don't want us to immediately consider internet speed. We want to start thinking about bandwidth as the maximum transfer rate on any network. The internet just being an example of a network. That make sense? In fact, most of the networks we deal with are synchronous networks. They're networks where the upload and download speed are the same. Only that one network that we deem to be really, really important deals with asynchronous connections, our internet connection at home. Okay, and here, this is actually something, this shared or dedicated question right here. I mentioned we'll talk about that when we compare cable modems to DSL. Whether or not the bandwidth that you're working with on the network is a dedicated bandwidth per machine or shared bandwidth per network across the whole network. Okay, DSL. So, this guy uses your existing telephone line. We talked about dial-up modems last time, right? Did I do my impression? I did that in here, right? What was that? What was that called again? When it's making all those beeping noises? It's got a real name. That could have been a good quiz question today. We talked about it. Handshaking. It's called handshaking. And why do we need a handshake?
Because you're converting from analog to digital.
Nope. I mean, factually, we are converting from analog to digital, but that's not the handshaking.
Isn't it like checking the line that you're using, like sending things back and forth to make sure you have a connection?
Ish.
Or it's checking to see how fast you can do it correctly, right?
Yeah, that's it. So it's the two modems that are talking to each other, negotiating a speed that they can send data between each other without having errors. And why is this? Because that predated TCP/IP, that whole handshaking model. We didn't have this bodyguard that made sure data didn't get lost back then. That's a much newer thing. And the dial-up modems used what network? What network did the dial-up modems use? I know it used copper, but I told you the name of the network last time. What do we call the telephone network?
It was something. Was it 56K? I remember.
56K would be the speed of a modem. What happened to my wheel? I'm looking for my wheel. Here we go. Oh, that thing's not. I think with some proper balance and a lot of glue. See? We move a chair. It just sat in here, so it wouldn't have happened.
Struggle's real.
What's up?
Struggle's real.
So what was it called? I can. You're. That's pretty close. Very close, actually. POTS. Plain old telephone service. POTS. Plain old telephone service. Okay, so I was about to look. Is it actually on the screen? That would have been really funny. Okay, so our old dial-up modems used our existing POTS network, plain old telephone service network, to go ahead.
Was it called that while it was in use?
Oh yeah.
Seems weird.
Yeah. I mean, it would have been something that the technicians that work for the phone company would have called it. It's not something that like my parents would have used when they were talking to me about it. You know, for them it was, the telephone line, something like that. But in the very early days of computer hacking, a lot of the stuff dealt with manipulating the POTS network. What's his? One of the original hackers. I think his hacker name was Crackerjack. Do you know what he's famous for?
Baseball song?
Well, how many of you have ever used a payphone? I don't remember the last time I saw one. Okay. How many of you know that payphones once existed? All right. So when you put more modern ones didn't suffer from this, but older payphones, when you put a coin in, it made a noise.
Just record that noise.
That noise was sent over the network to indicate that a quarter was put in, a dime was put in, a nickel was put in. Because the coin went in locally. Somebody had to come and empty those machines out, right? So that machine that telephone had to produce that sound on the network for it to know that a number was dialed. How many of you have, let's ask it the other way. How many of you have never used a telephone that had a dial tone? When you push the buttons, each button has a different sound, right? And in the earlier days, how many of you have never used one of the rotary phones?
I've used rotary.
I'm guessing most of you have not used a rotary phone. Only a couple of people have ever used a rotary phone?
I have.
You have.
I have.
You have.
So, yeah, right. So you haven't used one. Who else has not used a rotary phone?
Amish.
Well, Amish hasn't
You're
used
not allowed to
phones.
use
Yeah,
them.
he didn't.
We don't have phones. We have cans.
In the string, and we were
I got my
happy
eye on
people.
you, soup people. Have you seen that commercial? Okay. So when you have a rotary phone and you put in the number, and then the thing slices your finger off, right? Oh man, those things are terrible. That was how you got back at your parents. You sharpen them. You file that thing down. And, but if you listen, you go. You'd hear like the little beeping, and each one was unique based on what number you went to. Pretty similar. That's how these are how this is how communication worked in the early days of the POTS network. Okay? Actually, in the really early days, you just pick up your thing and there'd be a human being on the other end, and you say who you wanted them to connect you to, and they would connect a wire over. It's like, now you're talking to Bob. It's like, Bob, I have Mary on the line. Okay?
This is Steve.
Okay? I never had to, I have talked to an operator before, but it was never an automatic. I never just picked up the phone and said hi to the operator. I always had to push a number. Okay? But in any case, this Cracker Jack guy, what he's famous for is taking a whistle that came out of a Cracker Jack box and modifying it to make the tones of coins going into the phone. So he could pick up a payphone, use the whistle into the phone, and make phone calls wherever he wanted without paying. That was his thing. That was his superpower. Is modifying Cracker Jack whistles.
Now we'd have to struggle to find a payphone.
Yeah. So just kind of interesting history there. Well, anyways, DSL, digital subscriber line. So from our perspective, it's one of the options for high-speed internet, right? Okay. This guy used the exact same copper lines that our dial-up modems used on the POTS network. But instead of using a modem, which is a modulator-demodulator, which converts between a digital signal on your computer to an analog signal, which travels as a wave down the copper, and then gets converted back to a digital signal on the other end so it can go into the computer. Instead of having the data travel as a analog wave along the copper, it now traveled as a digital signal using the same copper, which allowed it to accomplish much higher speeds. But they had to use a filter. The reason they had to use the filter is what they had to do is they had to create two channels along that copper. One channel was for voice, one channel was for data. Well, voice does not actually take very much bandwidth. Do you know what kind of bandwidth is considered to be acceptable for voice? We'll go on the high end. We'll say 33.6 kilobit per second is considered to be acceptable for voice. Actually, not acceptable, clear for voice over a telephone. 33.6 kilobits per second. 4.2 kilobytes a second. It's not very fast. Make sense? All right, so you had to have a filter on the line so that now the filters are built into your modem. But before, you actually would plug a filter into the phone outlet. Well, you'd actually plug a duplexer into the phone outlet, so you'd have two phone outlets. One of them you plug your telephone into so you can make voice calls. The other one you'd plug the filter into, then you plug it into your modem. They call it a modem, not actually a modem. Because it didn't modulate, demodulate. It just digital to digital doesn't require conversion. It was a router, is what it was. So in any case, we use that existing system, existing telephone line, along with something called a DSLAM, which is the piece of equipment at the telephone company for supporting DSL. Now, DSL suffered initially from something called the final mile. See, is it on this slide, or can I make you guys guess? Okay, good. How many of you have heard of the idea called the final mile before? As it relates to DSL. You know what it is? Just kind of heard it at some point? How many of you have DSL at home or have had DSL at home?
In the past.
Okay. when you first looked into DSL, they probably had to come out and do a site survey to determine if DSL was available in your area and at what speed they could offer you. Okay, this was definitely true in the early days of DSL.
Further out you get,
Okay. DSL, the farther away from the DSLAM you are, the slower the speed it can maintain. All right, so for instance, when you go to AT&T's website and they show their DSL and they say up to, 12 or 18 megabits per second now is the maximum you can get. Maybe it's 18 megabits per second, something like that. You know, they're basically saying if you live next to the DSLAM, or if you live inside the DSLAM, we might be able to provide you with 18 megabits per second. Okay, but realistically, you have to be very close in order to get that. And even saying that, how many of you have UVerse at home? Okay, both of you have high definition. Okay, do you know how many high definition channels you can get at one time on yours?
No.
Okay, do you happen to know on yours? Okay, there isn't a plan. It depended on. UVerse uses DSL for video on demand or video streaming. Okay, so it's internet TV essentially. So it uses a DSL signal for that. Well, depending on how strong your signal was, you might be able to get 4 simultaneous high definition streams. You might only be able to get 3. You might only be able to get 2. So for some houses, they might say, oh yeah, you can watch 4 shows at once, but only 2 of them can be high definition. Another house might be able to watch 4 shows at once, but 3 of them can be high definition. Somebody else might be able to do all 4 at high definition. So for instance, I have UVerse and I can do 3 high definition and 1 standard definition simultaneously. My connection was pretty good, but not as good as it possibly could be. Go ahead.
Does that also mean that if you're watching TV and you have 2 TVs running 2 HD channels, and then if you try to get online, is that going to kill your bandwidth?
It's, well, no, because they set them up as 2 separate circuits. UVerse is considered to be a dedicated technology, so they give you one line dedicated to your internet TV and another one dedicated to your internet. So it shouldn't impact it. Although we'll talk in a minute or possibly next time about this idea of dedicated bandwidth is all made up. But in any case, so DSL uses that same connection, probably going to be a filter, and they say it's a dedicated line. That line, the speed of that line is going to be relative to how far you are from the DSLAM. In the early days, it was called the final mile. Later on, it kind of became called the final 3 miles as the technology got a little bit better. So you were able to provide the service to more people. But in the early days, you would literally have a situation where your neighbor could have DSL, and you couldn't because you were an extra 30 feet away. You were just that far away, that you were just a little bit too far away in order to actually establish a connection.
Story of my life.
Yeah, it's interesting. So, in any case, go ahead.
Just promoting neighborly love.
That's right. That's you steal their internet. Okay. So just to kind of give you the punchline with DSL, then, just so to kind of start wrapping things up a little bit. Typically, DSL is considered to be slower in terms of maximum download speed than cable. The proponents of DSL, they'll say that DSL is dedicated. So if you pay for 18 megabits per second and they say we can give you an 18 megabit per second circuit because you're actually creating a circuit between you and the phone company, a dedicated circuit to your house. So if you have UVerse, you have 2 dedicated circuits. Okay? But so you buy that circuit. If they sell you an 18 megabit circuit, they are providing you with a network connection between your house and the phone company. Okay, just like there's a network connection down there between those computers and the switch, the gigabit switch that we probably have in the office over here. Okay, that's the network they've provided. They said, well, here's a pipe, and it can send stuff at 18 megabits per second. That's a different argument than saying you have 18 megabit per second internet guaranteed. Those are 2 separate things. AT&T, using them as the example around here, as the phone company who offers DSL, they do not have infinite bandwidth. You know, they have a finite amount of bandwidth that they have to share between all of their consumers, right? Now, AT&T sells this bandwidth very much like hotels sell reservations or do reservations. A hotel assumes that a certain percentage of people are going to back out of the reservation. I think we talked about last time with like airline tickets, right? Airlines want to fly full. So if there's 300 seats, they'll sell 320 and hope to minimize the number of people they screw over, as long as they are flying as full as possible. Hotels do the same thing. DSL providers do the same thing. So they might have X amount of bandwidth, and they might actually sell X times 2 or even more bandwidth as dedicated circuits. And then they just cross their fingers and hope that everybody doesn't get online at the exact same time trying to maximize their internet connection and realize that they're not getting the bandwidth that they were promised. Does that make sense? Okay. Part of it is they can hide behind the idea that most providers can't pump out an upload speed fast enough to maximize an 18 megabit per second internet connection. Can't do it. In fact, generally speaking, the reason why we want faster and faster internet connections is so we can have more than one device doing networky stuff at the same time. Maybe we have Netflix streaming in 2 separate rooms. We have somebody else playing video games. We have another person Skype chatting. Well, each one of those applications takes up a portion of your bandwidth. Okay, so if you have enough bandwidth to go around, you can support all those applications without everything else slowing down. An interesting thing I had posted about last night, and then Tim seemed to think he trumped me, but he didn't. About you like, oh, did you see I posted about this? And yeah, I posted about it like 14 hours before you. Yeah, what do you think about that? So the FCC has changed their definition of broadband. And by the new definition, actually, I don't think any DSL would be considered broadband. What is it, 23 or 22.5 megabits per second? Some weird number like that. But somewhere in the 20 megabit per second, 23 megabit per second range is what is the minimum speed for a place to be able to say you are buying bandwidth or buying broadband. So 18 megabit per second DSL isn't broadband anymore as of last night or yesterday afternoon, whenever they passed the vote. So kind of an interesting thing. Again, in this example, notice that DSL is also an asynchronous internet connection. Your upstream is slower than your downstream. You know, here they're showing a downstream rate of up to 24 megabits per second. You are living in the D-slam. Okay? Your bed is hardwired to the D-slam. To sustain that, you have to be really, really close to the home office.
That's in office.
Yeah. You're on their LAN.
Yeah.
You have an Ethernet cable that's...
You're that guy with a camper right next to the building.
Yeah.
Just...
Yeah, and see, look, typically less than 10 megabits per second. Yeah. Okay, so the idea here is that it's really a misnomer. When somebody says, oh, DSL is dedicated and cable is shared, understand that becomes equivalent pretty quickly because of business practices. It would be a true statement if AT&T had 100 megabits to sell and they sold 100 megabits. So that your connection was guaranteed to be dedicated whenever you needed it. You had your 12 megabit per second. Whether you use it or not, it was there in its entirety. But that's not how they do it. They want to get as many customers paying them a monthly subscription as possible and hope that you don't get too pissed off. It's the game, right? Okay, that's fine. No big deal. And just to jump to the next slide real quick, which I assume is going to start talking about cable. Yep. Okay. The alternative here is cable modems say that they're shared networks. Okay, and we'll pick up there next time talking about the pros and cons of cable and actually May ask a quiz question on Monday. And the quiz question is going to, if I give a quiz, this is what the question will be, and it'll require you to do a little bit of research. Why did the early cable modems require a dial-up modem? Why did the early cable modems require that you also had a dial-up modem? You know, the old BP thing. Good quiz question. Somebody else has to remind me to ask that question, otherwise everybody gets zeros. And that person gets 3 zeros. Abe, you're my reminder. I got you a job. You, 3 zeros.
You got your
All right.
faith aspect of the course.
Did I? Oh yeah.
By
Ha!
existing.
All right.
So 2 zeros.
2 zeros. 10 zeros. 20 zeros. 2 zeros.